So let's go and take a look at this. Hopefully my screen shares. You guys can see that?
Yes.
Awesome. Awesome. It's a good day. So yeah, so we'll look at Frenzels, and then what I'll do is I posted Malvino's on there, so we'll spend the week with this part, and then like next week on chapter 36, and then and I do have, and see, having the internet out this weekend really killed me, but I'm gonna be posting up gradually. I'm gonna be posting up the practice problems for you guys, and we'll do that with. Thanks, John. Um, we'll do that with the operational amplifiers as well, because this is going to be an even little bit different concept, but we'll be going into the most famous op amp of all. This is like it's like the 2N3904, right? 3904 for BJTs is probably the most common one out there that you'll find. It's like if you cracked open most of your electronics and stuff like that, you'll find you just start going through and you go, oh, look at all these 3904s. And it's like, yep, they use them a lot. But the 741 is like that, where it's an extremely popular design. It's relatively cheap, has good performance. And then we'll start looking when they got inverting and non-inverting applications, and we'll go through that. And again, there's a whole set of golden rules with this thing. And Frenzel jumps right into it. Common op amp applications and whatnot. So just like with the differential amplifier, where we had the V1, V2, where we had basically it was considered an inverting input and a non-inverting input. And in a way to look at that, you'll see on the model or the op amp devices, you'll see two inputs. One will be marked with a plus sign, one will be marked with a minus sign. The plus sign is the non-inverting input, and the minus sign is the inverting input. And both have applications to it. And you'll find as we go through here that in some cases we'll have one or the other of the inputs grounded and just use the other exclusively. So if we wanted a non-inverting amplifier, we would do that, and then an inverting and do that, vice versa, right? So they have a single-ended output depending on what we put in as far as the input and how we configure it. And these have a classic style of configuration, but depending on what input we use dictates what the output will be. And you'll see we'll have two similar formulas, but they are different. And when you'll have a formula for inverting, and then you'll have another formula type for non-inverting. So basically, just based on what you see as the inputs will be which formula you end up using. And that'll be tied in with two resistors that they tie in with this. He calls it a little different, but I always call them RF and RI. Excuse me. One resistor is on the feedback loop, and then the other one is on the input. But you'll see it as we go through the configuration. And so the ideal op amp, right, has what they call an infinite open loop voltage gain, and remember, this is ideal, right? In the real world, this is not the case. That'd be awesome if it was, but we have a zero output and impedance, and then we have this basically, like I say, it's almost an infinite ground point, if you will, because the input resistance is so high. So if we look at a block diagram for it, right? So just remember how the differential amplifier is set up. And now we pull in a Class B push-pull emitter follower, right, from the power amplifiers. And these essentially are integrated together and create the op amp. So now notice on this block diagram style, on VN, there's two. So one of those would be the inverting input, and one of those would be the non-inverting input. And then how we have it configured will dictate how our voltage out is going to be. So if we were to look at it, so here's a classic symbol for it, right? Notice, and this is just like the with the power, well, with the power amplifiers, the emitter followers and stuff, where we had both a VCC and a VEE. Now, VEE is always the negative, right, which we're kind of used to dealing with, and VCC is always usually the positive DC. Well, this is the same case with these. So you'll have, it'll be like, it's a little IC package with 8 pins all together, 4 on each side, right? And it's not a very large device. And you just go with the spec sheets on it, which I'll also be posting, so you can, I know it won't be, this is the only drawback about not having lab, but you have the spec sheet for it, so you'll see how the layout is of it, and then how they have VCC and VEE, and then always, you know, just remember, it's like, okay, VCC gets a positive voltage input, VEE gets a negative, and then we have the 2 inputs of the op amp itself that are going to decide what our output is. So if you remember from the, like the differential amplifier model, right, we had the VCC and VEE, but we were taking the voltages across the 2 collectors there, and meanwhile had AC inputs to this. Well, that would be very much like this. So we're going to have 2 different inputs going into this thing, and depending on what we do with them is going to dictate what our output is going to be. So you see this equivalent circuit, and this is how we decided, okay, we have this Rn factor is going to be very, very large. Excuse me. And then, and what decides what our output's going to be. And in this case, he's taking, right, the AV of the overload and then just subtracting what V1 would be minus the V2. And this becomes a different formula altogether, actually. So these are some givens, that, if you will, that, like I say, Frenzel just jumps us right into this thing. So he's taking, all right, oh God. So he's taking some different things for granted here right off the bat. So we're throwing in what our frequency is, a unity, and this would be considered as a unity gain, where unity gain would mean that our AV would be equal to 1, if you will. But you'll notice that the AV that they have listed on the output side, right, is considered 100,000. Now remember, these things do have a what they would consider like an infinite gain, if you will. And what dictates that is how we're going to tie in 2 resistors with these guys, and that tells us what our overall gain will be. But let's take, for example, let's say here we get this, the VN is 2 millivolts, right? And it's an extremely small level. And then our output, if we had that as 100,000 gain factor, how much voltage we would be getting out when it would be, oh God, what is that off the top of my head? It's like 20 volts or something like that, which would be quite high if we're, especially since we have such a small signal we're going to put into there. And then we deal with another newer concept, which is the CMRR. This is something, okay, it's called, the abbreviation stands for, it's common mode rejection ratio. And now notice it's listed in decibels, right? And this is kind of why I've been emphasizing that we go through the Bode plots and whatnot, so you see what frequency responses are and how to sort of equate that to a circuit. Well, in this case, we have, which is, they call this is be our bandwidth, if you will, right? So we have a common mode rejection ratio of 90 decibels, which would be quite a swing if you remember from the Bode plots of how far that could go, right? So he lists off some things here that we're going to take for granted. And a thing to think about, like he says here, that we do have some BJTs, op amps out there that are used, but in a lot of cases, notice that we use the power amplifier as as part of the internals of the op amp. So what they decided to go with was more of a BiFET style or CMOS op amps, if you will. And it's just because of the large resistance factor. You got more stability, they can handle more before they blow up, basically. So, and then, yeah, like he says here in point 2, that these 2 styles offer a very, very high input impedance factor. And it is, if we were to, one thing we would do as part of our introduction, if you each had your own op amps, would be to measure and see how high your overall resistance value is of these things. And the reason being, it's a type of material they use, and B, it would be the way that they gated it together in sequence. The newer styles, they tend to go, there's a lot more stability to them as they try different materials with this stuff. So we have lower bias currents and offset voltages, which basically lead us to like less feedback. So we have less errors overall as far as our efficiency factors go with these things. And you'll find that the majority of op amps out there are highly, highly efficient, which is a good thing. And see, oh God. So these are like some of the pluses that you would have with given op amps, right? To say, great precision. You got a wide bandwidth, like in the common mode rejection ratio, where you had 90 decibels. That's a pretty wide bandwidth overall. So we would have a lot of room to play with, if you will. And what does that do for us? Well, a wide bandwidth, if you recall from some of the other amplifiers, right? The wider our bandwidth, the less negative feedback that we're going to have to deal with. And the less negative feedback we have to deal with is the less distortion. And the less distortion, the more stability. The better our overall signal comes in, or comes out, and the higher efficiency that it will operate at. And these are all things that we desire, right? You want a highly efficient circuit or device, if you will, with, minimum power loss and that kind of thing. So the less power loss we have, the less heat generated. Overall, the op amp it's a pretty nice device. And you typically, I mean, some of them you will have a certain amount where they'll be tied into heat sinks, and they will be in the can style. But a lot of them are just in the plastic IC packages with no heat sinks to them. They're fairly stable and really don't generate that much heat. So this is a classic circuit, if you will. Now notice he has both inputs to the op amp tied to ground, which make this nice and easy. It's like, okay, what are our inputs? 0 and 0. So as far as deciding what we have to deal with, it's pretty easy for the output, right? It's at 0. So he labels off, and this would be if we had the IC itself, okay? These are all the pinouts that are on the IC. So on the two sides, you have the VCC and the VEE. Your 2 and 3 would be your inputs. 6 is your output. And then you have 1 and 5 are kind of like what they call a slew rate adjustment, if you will. It allows us to control or give it a certain range, if you will, to try to basically set up for what our feedback range was going to be. I mean, having 90 decibel range is great, but at what frequency do you start and what frequency do you end? So you do have to set it up by like components to give us that range, right? So they're usually set up with, with 2 types of power supplies. You'll have a positive and a negative types, right? A lot of times they'll just have like voltage regulators giving you in a specific voltage to these things. Not a lot of current or something like that. Depends on your application overall. And like I said, your virtual ground is formed at the junction of these 2 power supplies. So those 2 pins in the middle there would literally be a virtual ground point. So he talks about so see, like I say, that's why I wanted to go through a little bit of an introduction with the differential amplifier like we did last week, because he just jumps right into it and assumes, and of course, he actually ends up talking about the differential amplifier more towards the end of this chapter. But in any case, so a differential amplifier has a certain amount of input bias and offsets that'll produce an output error when you have no input signal, okay? So that's like if you had both input signals tied to ground, if you will, and meanwhile you had VCC and VEE going, which means you're biasing the device, but with no inputs at all. It's just being biased, basically turning it on. Okay. So in this case, he says when the output error cannot be ignored. And so your circuit, why would you tie it to, basically, why would you tie both inputs to ground? That would be to see what type of error factor that would be produced, or like what kind of ripple you'd be getting out on your outputs, if you will, seeing how stable it is. So if you've seen like a nice flat line as your output, that means you have a fairly stable circuit without much error, if you will. Okay. But if you look at your ground line and you see a certain amount of ripple to it or something like that, well, that means you do have a certain degree of error. You might have to figure that in and see if that's something that you can deal with in the circuit, or if you need to do some further filtering or something like that to get rid of it. Um, so yeah, so he says that, yeah, by using the differential amplifier, you eliminate the bias current problem, right? By basically having the two opposing transistors, if you will, but you don't alleviate the offset current or offset voltage. So you will have to deal with those. A lot of times they'll tie in different resistor values and look at their gain factor overall. So if you had like too much of error going on, like too much ripple to the output, if you will, then you may have to reduce what your input's going to be overall. So yeah, each op amp and a spec sheet, and again, like I said, I'll post it up for you. They show you as part of the spec sheet a nulling circuit, and for that particular, so let's say the 741 always has a certain null factor to it, and it'll show you how to tie those inputs. Let's go back here. How to tie those inputs 1 and 5 in to basically reduce that null factor. Notice how they have a potentiometer on that. And so really what you could do is tune the circuit, if you will, and look while monitoring your output and basically try to drive down your the ripple effect as much as you can. Now with the simulator, we may not observe that ripple factor ideally, if you will, because it's already going to be assumed in. So the simulator is just basically going to crank us out the ideal amplifier. Whereas in reality, what we would have to do is basically you would have to tie this circuit up. You know, like each transistor had its own beta point, right? Well, these each, and again, we're dealing with linear circuit. So each one of these has like a tuning factor, if you will, where each one is not going to be a dead set range. Otherwise, we would just say, oh, just throw a 10K resistor in there and we're good. But no, notice it's a 10K pot. So each one has to be tuned marginally to just for what kind of ripple factor you can deal with on the output on pin 6 there. And that's the whole purpose of that. Yeah, so they, like I said, they have a nulling circuit given on the data sheet. And it's very much like this here, where if you had 0 inputs in with your VCC and your VEE tied in, biasing the device, right? So it's turned on, and with 2 zeros, basically, ideally, you should have 0 in the output. 10 times out of 10, you're not going to have 0 in the output, not a dead set 0. And that's where this little tuning circuit comes in for 1 and 5, is try to dampen that down, if you will. So he goes to say that the 741 has a common mode rejection ratio of 90 decibels at low frequencies. So this would be something to keep in mind, you know, like depending on the application that we're trying to throw this device in there. So if we look at this, right, if we have a common mode signal, so we crank in some sinusoidal of some sort at a low frequency, and we're talking like, you know, like a 1 kilohertz, 10 kilohertz, that kind of thing. We're not talking like in the case where we're dealing ultra high frequencies where we start getting into meg ranges and that kind of thing. Because what'll happen is if you recall from like the Bode plots, you do have a certain amount of range before it'll slew up. So your slew is that slope on the passband, right? So if it goes too low, it rejects it out. If it goes too high, it'll reject it out. But with a 90 decibel swing, we have a fairly large slope, you know. So if our input tends to be like a 1 kilohertz signal or something like that, we'll know we have quite a range to go on either side before we actually start experiencing any certain degrees of distortion or anything like that, okay? Yeah, so see in the very bottom point, he says in ordinary numbers, this means your desired will be approximately 30,000 times larger than your common mode signal, which is, if we tried doing that with like the small signal transistor amplifiers, yeah, not happening. I know this is a lot. I know this is a lot, and I'm sorry. And then just because, and you guys are all calculus experts, right? So that's what we're going to do now, just because you're going to love it so very, very much. But this is, take this with a grain of salt, if you will. Really what they're saying when they say dV over dt, okay, this is what you look at is you're looking at voltage versus time. And when you say dV to d over dt, what you're saying is all voltages over all times. So what it lets us do is basically it lets us set up a formula that would be applicable to any voltage over any time. Is all that means, okay? So then he goes down and says, okay, well, then here's our formula for this. And so you can see, okay, 2 fixed, right? Pi fixed. And our only real factors we would have in this case are frequency, which is an inverse of time, right? And then our voltage peak. So we should be able to go ahead and plug in then and find out, right, what this is. So if we wanted to find out in the case of the bottom formula, what's our frequency max overall? So what our power bandwidth would be in this case. So we can go ahead and quickly plug that in, right? Given that we know the frequency that it's operating at and our voltage. And that's all that this is applying, it really is, all it's saying. So this is sort of a fixed formula, if you will, and will be one of the formulas we can use. And you'll probably use it when you're going through the homework and stuff. And so then he jumps in. So with all that in mind, remember now, right? So we're dealing with a fairly good slew rate on this thing, 90 decibels. We have a virtual ground point, right? We have 2 different inputs. And then we have a way that we've tried to control the bias on it with those 2 pins with the potentiometer, right? So let's take a look at the inverting amplifier, which means we're going to use one of the inputs of the amplifier now and actually give it a signal. And the inverter is probably the most basic. It's probably the most popular used, that kind of thing. It does use negative feedback to close what they call a closed loop voltage gain. And that's a new concept for us, right? Closed loop voltage gain. What does that mean? Well, and you'll see from the circuit, we're going to go into a model because I can describe it better by giving you the picture. I always think a picture's worth 1,000 words, like they say. But in this case, we'll go through with these things in mind, that the closed loop voltage gain is going to equal the feedback resistance divided by the input resistance. And what this does, or what he's trying to do, is set us up for one of the given formulas for an op amp. And this is that example. So this right here is a very, very classic classic model of an inverting amplifier, right? So we use the inverting input, right? And then we have an input resistor, which is the first one tied in with the source there. And then we have that one tied in on that weird looking loop, if you will. So we're literally tying a resistor in to both the input on one end and the output on the other. All right. And so what they call that is a feedback resistor. So if we were trying to control our feedback, right, this would be the one. So the formula sets us up, and see, I always call it RF and RF. And since we're using the inverting input, the formula literally is minus RF over RI. It gives us a ratio. And let me go into that here. And that's what he's going through here. So if we want to figure out what is the overall gain or gain factor for an inverting amplifier, this is the formula. This is a golden formula that will always be used whenever you use an inverting amplifier. It was always minus RF over RI. So your values of your resistor here determine what your gain factor is going to be of a closed loop. And by loop meaning this. So our loop literally is following around. We have the input going into the output through the device, with a feedback resistor here. So this provides what they call a closed loop. We have no outside influence coming into it, okay? This literally will take the output and mirror that back to the input and vice versa. And this constantly goes through in a cycle. And of course, you know, just like we had with like the emitter amplifier, the inverting input is going to invert the output, right? Literally. So you're 180 degrees out of phase with your input. And that's what this sets us up for. And this is always a golden rule with these guys. Basically all three of those, right? So this is like applications of Ohm's law and throwing in the gain formula, if you will, where the gain, right, is always equal our output voltage divided by our input voltage. And we look at V out is equal to our current times our resistance. And so in this case, see where the current flow goes. And this is an interesting thing, right? So notice how the current flows through there. Now at these 2 points, yeah, see how that imaginary ground symbols drawn there, like silhouetted, if you will. So from these 2 points right here is literally a virtual ground. And remember that. So in certain cases, what would happen if I had a ground point at this point here as far as how our current's going in, right? It's a strange little concept, if you will. Is that would these 2 resistors be in series or would these 2 resistors be in parallel? And that's a thing to think about. So, but let's watch our current flow. So we have IN coming in with the voltage in, right? And the IN continues to flow here, but our voltage in does not. Our voltage in goes into the device. And that is because of this virtual ground point. So if we say that the VN is equal to IN times R1, which would be this here, right? And then our V out as a relation, it's inverted, right? So we would take the negative factor of IN times that RF right there. And that's just Ohm's law for those bad boys. And then what do we look at here as far as he says the closed loop, right, of R1 is this impedance here. And we'll get more into that in a bit. It's a crazy concept, but that's one thing they can use with the op amp is because we literally have that virtual ground point, because our resistors are never going to be anywhere near the range of resistance that's going to be provided on the inputs of these 2 guys, okay? And so we look at our response to this thing on the closed loop bandwidth, and we could see it's quite the range. Look at that. We can literally go from 10 hertz up to a megahertz with this thing, which is insane. And I mean, and that's without much distortion. Whereas if we tried using any of our other amplifiers that we had a very tight bandwidth, if you will, where our bandwidth is on this thing is quite large. I mean, 10 hertz to a megahertz is quite a range. And there we are, right? So our overall response, if we look, yeah, we're about 90 decibels, right? If we go with 100 decibels being our cutoff there, all the way down to 0. So yeah, that's it's kind of crazy how much range that we do get out of these things. But get used to that. That's the beauty of using these things, and that's why everybody loves them so much. Excuse me. So something to keep in mind. If the negative feedback is going to reduce your output error, right? But by the input bias current, the input offset current, and the input offset voltage. And these are all because essentially inside the heart of the amplifier is we're dealing with those 2, where we have the differential amplifier and we have the class B power amplifier, push-pull. Excuse me. So we'll use offset nulling to try to, we're basically, when we're pushing this op amp to its extremes, we try to use the offset nulling, which is that potentiometer, right, to basically try to control the amount of feedback that we'll be dealing with to keep the ripple factor down to a minimal. So if it's necessary, like he says here, if it's necessary to compensate for your input bias current, you'll have to come up with an equal resistance connected to the non-inverting input. And so he's saying right there, you would have to possibly have some type of resist factor tied into that instead of just leaving it as a straight source to ground. And what that would do is set up basically any ground bounce that you would have, you know, trying to control a ripple factor, if you will. We don't have to dwell on that a lot. I'm just, it's just a point. Like I say, you know, Frenzo's things, he just assumes a lot of stuff. But in any case, so if we look at our next slide, yeah, that's essentially the same circuit, but notice that we have a resistor, an air resistor plugged into there, if you will. And how do they decide the value of that? Well, throw these two because of the ground point, throw these two into parallel, come up with the equivalency, and that's what your number. And so what it would do, see how it's trying to basically balance both sides resistance wise, if you will. So that way it would control any kind of feedback that you would have on your virtual ground point, if you will. And it's just an engineering point. And like I say, you would have to really be pushing this thing to its like extremes, if you will, to really require having to use this. But if we were driving it and we were getting a certain amount of distortion to our circuit, this would be a correction factor that we could throw in, and it would help balance out our circuit. So then, is this going along okay with you guys? I mean, am I killing you? I know it's time for a nap, right? No. But I mean, really, the two styles, and as we go through these design concepts later on and stuff like that, really all we're ever dealing with is the inverting, where we have those set of golden rules, and really are the major one to come away with on that one is knowing that the AB is going to be equal to minus RF over RI. And then in a non-inverting amplifier, as we go through this one has its own other formula, very similar, but a little different. So he, because of the style, and one of the things to note here is one of the golden rules they have is that E plus equals and follows E minus. Follows, okay? So this is something to keep in mind with these things when you go into this non-inverting style. Now notice this, the way we have this set up. So on the inverting input, now we have another, right, closed loop again, and we have an RF and an RI, and that RI is tied to ground in this case, and then our non-inverting input is coming straight from the source. And the output, of course, is in phase with it, okay? But the way this looks at it, it's a little different. Now remember, we still have that virtual ground point being tied into here, okay? So if we had a virtual ground here and we had ground here on this thing, how does that balance the circuit out, right? So that's something to keep in mind. And again, we still have what they call a closed loop. So we do have an input being tied into the output in this case. But notice, just as a similar thing here, that we're still using the non-inverting, right? And that's because E plus equals and follows E minus. So we have to take that as a factor. So we come up, we do some math, and we look at, because of that virtual ground point being established here, how do we come up with our overall gain factor? Well, we look at RF plus RI divided by RI, right? So we do the math with that. Again, you won't have to do this, but this is our golden rule that the AV of the closed loop AV of this circuit is always going to be 1 plus RF over RI. And that's for a non-inverting amplifier. So those are like two golden rules. We have an inverting amplifier golden rule, a minus RF over RI is equal to your AV. And then a non-inverting golden rule is 1 plus RF over RI is equal to your AV. And what this does is it sets us up like design factors, if you will. Like, let's say I wanted to have a specific gain, right? Then I can go through and plug that in and establish what my values are going to be for my feedback and my input resistors. And then what dictates our voltage out in this case is a little bit different, if you will. Notice in this one, our Ohm's law derivation comes out to, now we have I1 being established here, but with respect to both RF and RI, where before, let me go back here, right? We were just looking at what was being established with the feedback resistor. So the way we tie in those inputs does change the way that we have to look. It's still driving that current, right? Current follows the least path to ground. Boom, boom. In this case, it's going this way. And a thing to remember that your Z in is infinity. Reality, no, you will find an actual value for this thing. Yeah, it's usually in the mega ohm range. Very, 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 very high. And so he kind of takes, and with those in mind, we kind of look at what are some common applications. What could we, okay, we know this now. What the hell can we do with this? And why? What do we want to do with it? Well, they have something they call a summer, where you sum up two different voltage inputs, if you will. So a summing amp has two or more inputs and one output. Each input is amplified by its channel gain. And if all channel gains equal unity, where your gain is 1, unity is 1, the output equals the sum of the inputs. And this is something that they use a lot for stabilizing, like, with microphones or musical instruments, because unity gain is basically reproducing the signal without the degrees of distortion. So you get minimal feedback, if you will. So here would be a common voltage summer, where we would take literally two different voltages and throw them in together and have this thing amplify them, if you will. And the way we look at it, just an Ohm's law application for both of them, right? So our RI in this case is actually two different resistors, and we have the closed loop with a feedback resistor right here. And don't worry, I'm going to go through the Malvino interpretation of this on Wednesday, because this is going to be a lot of stuff, new concepts, and Frenzel's approach is always unique, and it's a lot of information. But what this would do is we could literally take two signals in and amplify them together. And another one and that's just a summing amplifier. So when you see that, that's what the type, there could be more, and actually you could even have more. You could have a whole cascade of different inputs, if you will, okay? Don't worry about that. We're just gonna look at another type as well. There's something he calls the voltage follower. And this is another application. And if you remember from the transistor model, we had an emitter follower, but this one, well, like he says, it works much, much better. And we have a closed loop gain of unity, which means unity, our gain is always going to be 1. And in this case, we have a bandwidth that would have the unity. So this one is good for if you had a high impedance source with a low impedance load. So something where real high on the input and real low on the output. And this would be like your go-between circuit. So we can look at it, and it's a fairly simple circuit, if you will. And because we're going with the unity factor, there are no resistance values, if you will. We're literally just relying on the op amp's internals and pumping an input into it. Just remembering that between these two guys, we have an infinite impedance, and that sets us up and establishes our output here, just straight based in, boom. I'm sorry, I know. We could talk a little bit about this. They do have, now here's an interesting thing, and remember SMDs are very small package sizes. So you wouldn't expect to see an SMD being used like in power applications, if you will. It just wouldn't be able to handle the heat factor. And again, because SMDs are depending on which style there is, there are several different package styles that they come out with. So depending on the number, depends on what size it'll be and that type of thing. You got SOPs, SOICs, and these are just different package sizes. And so one thing to note is that the SOP is your usual preferred SM style just because it's the larger. But there are some where like small signal amplifiers where you would have an SOIC style. but you won't see too many of them really. Now here he goes into using the op amp as a differential amplifier, if you will. And he just kind of jumps into this one. Where basically what we're doing is taking the difference of the two voltages. We're going to pump in two different voltages and see how we have our feedback resistors tied in. So here's our closed loop one right here. And the closed loop would be from both sides, right? So the way our inverting and non-inverting inputs look at this, this is always considered a closed loop right here. So you have to be careful when you do the math with something like this. And the common mode rejection ratio steps down quite a bit for this guy. And notice that our output or our output gain is the inverting formula, because we would take the minus, right, RF over RI. But in this case, he's saying R2 over R1 on the inverting input. And then notice how we differentiate between R1 and R2 with the prime hashtags right there. So you'd have R1 prime and R2 prime to be able to figure out anything with your overall circuit. And ideally, these do equal. So you'll have these both set at the same values. There might be times when you would have them different, but then your differential would have a certain amount of feedback to it, a little bit of noise because it would be imbalanced. But usually you set these both values to the same and then can compute your output as this. And that would be essentially how you would look at it and how you would set this up. Yep, sets us up for something called a transducer. And we'll get into that a little bit later, actually. We'll start looking at SCRs and transducers. And these do have real world applications when you get out there. And what would they use a transducer for? You could have different like noise measurements going on. They use them for like stress tests, if you will, where if you have a certain amount of like weight or something like that, or a certain amount of pull. Oh, I gotta look at chat. Yeah, like that as well. Aaron said sonography. So transducers, yeah, so they do have a certain amount of, you will run into them out there, and this is generally how they have the circuit balanced out. And you see it's a difference between the two, and it's how you would measure. Like if you had that one side weighted to the other side in normal operations, your V out would be a 0 volts, right? But the minute the value of the transducer started to change, it would change that voltage difference, and then this side would become difference compared to this one. And they usually set devices to measure, and it would be a digital readout for you, right? Even like a tuning thing or whatnot. And you'd go, okay, I'm starting to see some stress here. And in a way, the amount of voltage change to the factors, if you will, like weight or pressure or sound. They have a lot of different usage, and the Wheatstone Bridge is extremely popular. They use it for so many different types of like measurement circuits, balance circuits, because both sides, when nothing happens, equal out, right? You have nothing happening. It's easy to tune it. So really, when you go through and tune something with a transducer in there like that, what you're ideally doing is getting your voltage readings to balance out on both sides to 0. And that way, the minute you start doing whatever kind of work it's expecting to see, you start creating that resistance imbalance, and it'll change that voltage, and then they just read out the difference of that voltage and make a measurement, if you will. And there's a lot of different applications for that style, which is kind of cool. And it's usually small. You're dealing with like usually millivolts while you're trying to track it through. Yeah, and I forgot the temperature factors as well. Like if you're measuring like I don't know, it could be temperatures for so many things, even like simple things like water. If you're watching temperature of water change, that type of thing. Excuse me. But essentially, that's most of his stuff. And he gets into, he throws a couple. I'm going to do some labs too, but we'll look at Malvino's approach to it. And that way we can get a little better idea of some of the math behind these. But we're going to do labs for all these too, some not too complicated ones, and look at some of the factors for these different types of amplifiers and what goes into making them. And you deal with an instrumentation amplifier, right? And these have a lot, what they call a large differential voltage gain. Now we should be used to that term by now, right? Differential. So we're looking at the difference between two voltages, if you will. And this one has, in relation to a lot of the amplifiers, we have a high common mode rejection ratio. So meaning we have a great degree of bandwidth to this thing. And overall, this it's a fairly stable. Yeah, here you go. It's a pretty simple circuit, right? No. So this kind of culminates from everything up through the chapter, and we'll get into this gradually before we get actually to this point. It's sort of a balanced circuit, if you will, and figuring out your overall voltage gain as our output takes a certain degree from looking. If you notice, we're using the non-inverting inputs of both of these guys, right? So we would have to take that factor in for our closed loop gains here on both of them, and then figure those both in as we use. And again, here's your closed loop of this guy, but we're using both of these here. So really we're taking the concepts of everything up to this point and combining it all and coming out with this guy as our final. And so this will be like the culmination of the chapter as we go through, and it's like, okay, so you had the inverting, you had the non-inverting, we have voltage followers. No, let's just throw that all together and do this. But that's why I don't like Malvino's approach. He just kind of jumps right into that. But there are applications for that style of circuit as well. Like I say, the instrumentation amplifier, and you'll see it used a lot for different devices out there where you need a good amount of stability. But yeah, and again, you get that input. Yeah, look at the input impedance on this thing is like 100 megohms, which is huge. So you never have to worry about it shorting out. Usually things from the outside won't affect it, like if you accidentally crossed wires or something like that. And we'll look at also like single supply operations as we go through this thing. Yeah, this one's a fun one as well. Now we throw in capacitors with these guys. And essentially what we're doing is making a voltage supply, if you will. And this is where it culminates. He's at the end of his chapter right here. So we won't get real deeply into the single supply operation at this point. Just note that it's out there, and we'll jump more into this type of thing in the next chapter when we go into 36. But this would all be considered linear applications, if you will. And then we'll start looking at non-linear applications. It would be the next chapter. And like I said, this will be a lot of concept, but I'm going to throw, oh God, I got so much stuff. I'm going to throw a lot of stuff on Blackboard today. And we got the quiz for chapter 37 we're going to do. And then we'll be going through, and I'll be posting the homework for chapter 35. I want to get some practice problems going up. I especially want practice problems for each of these, like certain style circuits of these guys. We'll want to really practice like the non-inverting one versus the inverting and get used to those concepts of how that works with the formulas. Because this ideally would be a formula you would want to know. If you come away with anything from op amps, would be these two formulas. E plus equals and follows E minus. I plus equals I minus, which is equal to 0 typically. And then these three formulas, these two formulas of AV for non-inverting and inverting. And I'm sorry, I know this is a lot of cut and dried stuff, but that's like Frenzal's approach. I'm gonna stop sharing that too. But we'll look at Malvino's approach to it on Wednesday, and we'll go over some other things. I'll post the homework for this, like I say, start getting into it and seeing how these things work. And again, these are all things that are used, out in the work world that you're going to run into, like the power amplifiers that we've seen, the small signal amplifiers that we've seen. These all have relevant applications out there. And for the op amps, we use that in so many things, voltage supplies, any type of measurement devices that you see out there that you'll be commonly using. And I'm talking with all your instrumentation that you use out there when you get out in the work world, right? It don't matter what type of industrial electrician you're going to be. you're always going to be running into instrumentation, and basically all your readouts and whatnot that are doing measurements are utilizing some of these circuits here, really. But that's what I have today for the lecture. I love Frenzels. Just jump right in there and let's do this. But like I say, I'll post we'll get a formula sheet going for our inverting, non-inverting, and then we'll have the different styles like the voltage follower, the summer, that comparators, and so on as we start getting into these. Because each one of the cool thing is these are like classic circuits. So the only things, once you get used to the model and the formulas for it, right? The only thing that's really going to change are like values of the components and what your outputs are going to be, that kind of thing. So it'd be like, okay, so what's your common mode rejection ratio for this circuit? That kind of thing. But as far as the circuit itself goes, they always follow a golden set of rules that never change, which is a nice thing. And yeah, and the op amp does have it's got a pretty good degree of stability, which is real nice. So we don't have to worry about as many correction factors, if you will, compared to like the transistor amplifiers, where too much negative feedback would kill our signal. These guys handle quite a bit. But you have any questions on this? Is that all good so far?
So all this homework that you're gonna dump on us on Blackboard, when's it gonna be due?
What for the homework or the quiz? Wait, what? What?
The homework and stuff of that nature.
Oh, probably just sometime this week. I won't make it like immediately due. It was my fault. The internet was out, so I'll have to we'll do some adjustment for it. But yeah, we'll do a chapter 35 homework. I'll post up, and then I want to post up the chapter 37 quiz. I also want to go through. I want to have the video demonstrations for the other labs. I got to get on there, and then we'll get some new labs on there as we start getting into these op amp circuits. And a good thing, I mean, as far as the simulator goes, it does. I was playing with it. It does do a pretty good job of doing op amp applications, so we shouldn't have too much trouble with it. And the Bode plots do come out pretty nice with it now. So yeah, we won't make this like immediately due, Jared. I'm not gonna try to kill you guys. I'm not gonna take real long because I want to get through chapter 35 is for this week, and then we want to do chapter 36 for next week, and that way we can start jumping into. We still got our oscillators, thyristors, and then I want to at least be able to get into SCRs, if you will. I don't know if we're gonna we might take a look at like regulated power supplies, but not real deep. Really, our most thing out of this is essentially this class would set you up as getting used to like radio concepts and instrumentation concepts, if you will. So by doing oscillators, we could generate our own frequencies, right? So that way we could even set up, like if we had to, our own radio and power amps and things like that for even like music. And then these op amp concepts with the SCRs and thyristors, that would go more in hand with how instrumentation works, how you're getting your values for instrumentation that are doing measurements and that kind of thing is my goal with this. So yeah, I'll probably have the homework set to do later on this week, like Thursday or Friday or something like that, I guess.
Okay.
But everything else going good? You guys have any other questions, or is there anything you need me to go over, or anything? I feel kind of out of touch because I don't see you guys all the time. I actually look forward to spending those 2 hours of lab, like I was talking with Cameron earlier about, that we're kind of missing where you don't get the setup.
And those will be up tonight.
Yeah, I'll have the labs and the homeworks up and the quiz up today for sure.
For the previous labs, I don't see any grades. Have you graded those at all?
No, I got to go through. I haven't had access. I'm going to go through. I got a hell of a day ahead of me. I'm going to go through those today as well for getting on Blackboard finally and getting it all posted. I'm sorry. Yeah,
Okay.
my internet was kaboosy over the weekend for some reason. I don't know if you guys have ever dealt with Frontier Telecommunications. They do, I guess they're the remote region telephonies provider. Because they have cable. We don't have cable out here. They have cable in my nearest town, but that's like about 5-6 miles away. And for some reason, they won't bring it out here. Sorry. But no, I'll get, yeah, I got to go through the labs, get all that posted up and all that. Definitely. I'm sorry. I had all this stuff I was going to do over this weekend and have everything all on track by today, but that did not work for me. But no, I'm going to go through it today. We'll have it all, basically, hopefully everything will be all on track and up to the dates that I wanted to be by, by tonight. Okay.
All right.
So everybody else doing okay out there? You got, I know Brenna's still working a lot out there with all this craziness.
Every day.
You guys keep it safe out there. And
Only thing that changed is school.
yeah, I guess we're still, yeah, I guess they plan on the summer semester is also going to be an online approach. There might be a couple of add-ins for things and stuff like that if we're going to get deeper into it. I know from my residential class, I'm actually putting together a parts list, like all basic, like wiring stuff that can be put together like a package and given to the students for that. That was my only thing I was missing was a hands-on approach for residential.
Yeah, that should be a fun class to teach online.
Yeah, it's
Yeah.
really. It's not.
John's been struggling with industrial.
Oh, I heard industrial is literally a monster because even trying to think, there was a simulator software out there for it, but again, we didn't have it, and that's something that they may be getting. But even that, I mean, it's still as far as like trying to do relay logic and stuff like that, how to wire things up, because you can draw ladder logic and stuff, but to get that concept across, so okay, this is your ladder logic. Now go make it a reality. Right, you have 150 right now, or you're taking that?
I've got 150 right now.
I bet you that's So how is he doing that? More like a demonstration approach, or what?
Well, so far it's just been videos and concepts, and then when it comes to ladder diagrams, he's having us draw them out. So
Okay,
he's working with that.
awesome.
Who's teaching that, John?
Yeah.
Yeah, John's.
That's unfortunate you guys are missing that with him, though. He does pretty good in class on that one.
Yeah, he does. I was going. He actually loves that class.
He does.
I know. Like I watched him the one day. I was like, oh my god. And I mean, I like that. That's actually a fun class, actually, getting into all that relay logic like that.
Hmm.
And then if you ever want to actually, if you ever have the misfortune of seeing what they came up with for relay logic before PLCs came along, you can work in some of these factories or warehouses where they have old instrument panels. Because like Caterpillar still had a couple of machines where it was all push button, all relay logic, where normally you'd have the PLC and you just go through and press a couple of buttons, set up some timings, and you're done, right? But the old relay logic ones, it's like, okay, after 10 minutes, press this button. And 15 minutes, press this one. Now this one, and now this one. They had a couple of machines where they only had a few old guys left that still knew how to operate them just because of the sequence involved. And the instruction set was like a couple of hundred instructions on how to manually operate this thing. And that's when you get a real appreciation for relay logic, right? I mean, we still use them a lot out there, but it's the PLCs with their input output boards taking away a lot of the pain of the control side of all of that. But yeah, it's something. It's what they did back in the earlier days, 30s, 40s, and 50s. It was all relay logic for your automation. But no, that's good stuff. I can't imagine I wouldn't want to try to do that. But no, for residential, it's going fairly good. Well, I mean, 'cause the main goal of residential is to teach you the code. My only drawback is just like certain proper techniques and, what the specialized tools are, right? That was always my biggie, it's like, did you know that your wire stripper is a multi-tool? No. And did you know that your lineman pliers are a multi-tool? And I, given demonstrations of that and stuff, but yeah,
A lot of channel locks make good hammers, so that's a multi-tool.
what?
Hey, Analog makes a pair of pliers. That's a hammer.
Now, see, when I was an electrician, the one tool that was never, ever, ever on my belt, on my pouch, right, was a hammer. Hammer is in the damn bag because that's how often I needed one. And it's like an electrician with a hammer is as scary as like watching a carpenter with some wiring, right? I don't know. That's just the way I was. I was always done up with. I did electrical work for a long time, and no, you don't have a hammer. There ain't no need for a damn hammer. Even when I was out there in industrial electrical, my hammer wasn't on my pouch. I had a screwdriver multi-tool, the 10-in-1, which the Milwaukee one is really cool, by the way, if you ever want a really good 10-in-1. I had an adjustable wrench. I had wire stripper multi-tool, and what else did I have in my? Because I had a little mini cheater pouch. Because it's hard to get up and down those ladders with a bag and stuff like that. But no, my hammer was always in my bag, and even then, I never had a clawed hammer. There was no way in hell. I always had a mechanic's hammer, with the ball peen end and the big pounder in, my metal beater. But no, electrician and a hammer. No, I'm a firm believer in not. And that's my approach to electrical work. Shouldn't have to have a hammer. Anything that you're required to drive in and whatnot, you have your cordless. I never nailed anything on. I screwed it on because I didn't want it to come undone. Nails over time come loose. You screw it in and it stays there. Yeah, anyway. But no, I was an electrician for almost 20 years, I guess. Let me think. No, electrician probably from about 1979 to about 1993. So no, it was like 14, 15 years. And then I went and did school electronics and got my bachelor's and went out to Silicon Valley in California, and that's where I learned all my electronic stuff and semiconductor. So I've always, I don't know, since high school, I've always been doing electricity. And I could tell you right now, no hammer. And then I even controls and instrumentation technician. I never, no hammer. No hammer. You ever had to pound something? You had your lineman pliers usually were about enough to whack something in. I don't know. That's me. That's how I teach. Don't use no damn hammer in my class. I'll get you points taken away. A little different out here in the countryside, I guess. Where I'm not a big fan of Romex either. I hate that crap. I think Romex is junk. My boys, I like EMT. Anyway, I know I'm rambling, right? You guys are just all listening to me, but no, that's the one thing I miss about in residential, because there's a lot of demonstration stuff and how to properly splice things and strip things and whatnot. I'm real big on that kind of stuff. So whenever I open up a box, I can tell if a non-electrician has been in there or not, and the way it's all put together. First indication is total lack of any black tape is my number one. It's like, okay, even if you were an electrician, you do not know what the hell you were doing if you did not use any kind of electrical tape. That's one demerit right off the bat. And you'll use it in industrial world too. I used to yell at guys, so you get a big ass, your 3-phase AC induction motor, right? So you're going to go through this 480 volt motor, and you're going to go into the enclosure, right? The pecker head where all the wires are. And you're going to start splicing these wires together for high or low operation, right? And bringing in your main power feed. And so 9 times out of 10, well, one, those should be, you typically like crimp-on connectors that you attach those to, but some people go ahead and use wire connectors, just the screw-on types with no electrical tape. And what's the number one thing that this damn motor is going to be doing? It's going to be vibrating because it's always running. And then what happens with your connectors with vibration is they start to back off. And I swear to God, it's like, okay, you're going to kill somebody. But always wrap, your 2.5 loops of electrical tape to keep that from happening. I've yelled at guys for that. Yelled at them. But it's one of the big things you learn in my residential classes, how to properly wrap stuff. Strip it, wrap it, how much is too much excess and all that kind of stuff. Anyway, but all right, I'll quit rambling, and you guys are all
I have a
good.
question for after you're done recording.
For after I'm done recording. All right, I'll turn off